All right, so welcome back to enclosure fire modeling. We're going to start the discussion on VentFlows. This is module 7, part 1 of the discussion on VentFlows. Our purpose here is to review the basic concept used in the description of the mass flow rate through vents in systems that are exposed to natural ventilation, where the flow is driven by buoyancy. From a zone modeling perspective, our goal here is to establish expressions for the mass flow rate m dot in and m dot out. As you may remember, in our governing equations, we have different flow streams. We have the fuel mass loss rate m dot f that is required. We have the mass flow rate of air entrant from the lower layer into the upper layer m dot a that is required as well. And we have m dot in and m dot out that so far we haven't talked much about and that are required to describe the exchange of mass between the room, the fire room and the exterior. All right, so this material is discussed in the chapter 5 of the textbook, and you have also here 2 chapters from the SFP handbook which bring additional detail. So the basic description of mass flow rates through vents is based on the Bernoulli theory, the Bernoulli equation. So here you have a reminder of the Bernoulli equation. If you draw a streamline from a point A to a point B, you can write that the total energy of the flow, meaning the kinetic energy per unit mass plus the pressure energy plus the potential energy that measures the energy associated with elevation, is conserved to first order, if you neglect losses, is conserved as the flow goes from A to B. Okay, so the total mechanical energy of the flow at A is equal to the total mechanical energy of the flow at B. Okay. Now, if you do some simplifications, for example, if you assume that the change in elevation between A and B is small, so ZA is roughly equal to ZB, if you also assume that the flow surface area at A is much larger than the flow surface area at B, which means that the velocity at A is much lower than the velocity at B, so that you can neglect UA square when compared to UB square, you are left with a simple equation that relates UB to the pressure change from A to B. And this leads to the well-known Bernoulli velocity expression as square root of 2 delta P divided by rho. And this provides an expression for the mass flow rate. The mass flow rate is mass density rho times the Bernoulli velocity square root of 2 delta P divided by rho times the surface area of the vent A sub O, O for opening here. We typically add a flow coefficient CD to measure deviation from idealized Bernoulli theory and to account for unaccounted for losses. Okay. So we're going to use this equation. Bernoulli relates the mass flow rate to a change in delta P from A to B. And the question is now, how do we express the change of pressure as we go from A to B? Where we are going to use hydrostatics. And in hydrostatics, the pressure changes with elevation only. And the delta P is related to rho g z, okay, where z is elevation. And so we are going to have to be very careful about the rho. The mass density at A is different than the mass density at B, which explains the pressure change as we go from A to B. And in the context of fire modeling, the mass density of the gases inside the fire room are much lower than the mass density of outside air. And this will be enough to create some pressure changes that are going to be driving the flow. Okay, so the next few slides describes a typical developing fire with the smoke buildup and the descent of the smoke from the ceiling towards the floor, and shows on the right the effect of this smoke buildup on the pressure. So on the right, you are seeing here two pressure profiles, P inside PI and P outside PO. These pressure profiles are plotted as elevation versus pressure. So you have pressure on the x-axis and elevation on the y-axis. This is the standard way of plotting these profiles. And so what you see in these profiles, first, let's look at PO. So we say that the pressure outside is a linear curve because the change in pressure outside, delta PO, will be proportional to the mass density of outside air, rho times Gz. We also see that this change in pressure is such that the pressure decreases as you go to higher elevations. Okay, so pressure changes from floor to ceiling. Now let's look at the PI, the pressure inside the fire room. Well, we see that this pressure inside the fire room, first of all, is higher than the pressure outside. Okay, and is higher than the pressure outside at all elevations inside the fire room. And this is the situation that is found in the early phase of a developing fire, where as you release heat inside the fire room, the pressure goes up. Okay, remember the bulk pressure equation, the equation for P bar that we discussed in module 2. So the pressure goes up because of the heat release rate of the fire. And that means that there will be a natural tendency for the heat release process to drive the pressure to high levels. And the pressure inside the fire room will be larger than the pressure outside. So if PI is greater than PO, we can expect outflow through the open vent because the flow will go from high pressure regions towards low pressure regions as predicted by Bernoulli. The other comment I can make here is that the pressure inside the fire room is not a linear function anymore, but is a piecewise linear function. And we see that we have a change in slope at z equals zd, where zd is the elevation of the smoke layer. So at z smaller than zd, the pressure inside the fire room changes with rho as rho gh, and with rho being the mass density of the lower layer. Now, if the mass density of the lower layer is roughly equal to the mass density of fresh air outside, because the lower layer doesn't heat up much, then we see that PI and PO follow parallel curves. On the other hand, if Z is greater than ZD, then the elevation of the smoke layer, then the pressure inside the fire room will change like rho GH, rho GZ, where rho now is the rho of the upper layer. And this explains the change in slope in the pressure profile PI for high elevations. All right, so in this stage 1 development of the fire, this early phase of the fire, the pressure inside the fire room is higher than the pressure outside, and we get outflow of fresh air through the open vent. Then we move on to stage 2. As the smoke builds up, keeps building up inside the fire room, the smoke descends towards the floor, and at some point, the smoke will reach the upper portion of the open vent, and therefore now the vent will be a place where we expect outflow of fresh air at low elevations, but also outflow of smoke at higher elevations. And so stage 2 really looks like stage 1. We still have PI greater than PO at all elevations inside the fire room, but now instead of having outflow of fresh air only, we have outflow of fresh air and outflow of smoke for Z greater than ZD. So stage 1 and stage 2 are basically two early transient stages in the development of the fire. Then we move on to stage 3, and stage 3 could correspond to a steady state, to a state that is maintained for a long time. So we can see that the smoke has descended further inside the fire room, but now because of the equilibration of pressure between the processes that drive pressure up inside the fire room and the vent flows that tend to decrease the pressure, now we are reaching an equilibrium in the pressure changes between the variations inside the fire room and the variations outside. So we've reached a steady state. And the two pressure curves that we can see on the right here now have an intersection point. And this intersection point is called N at an elevation Zn and is called the neutral plane. The neutral plane is defined as the place where the pressure inside is equal to the pressure outside. At that location, because Pi is equal to Po, there is no flow. At locations Z higher than Zn, the pressure inside the fire room is higher than the pressure outside, and we expect outflow. So we are going to have outflow of smoke for Z greater than Zn. At locations smaller than Zn, at Z smaller than Zn, we have Pi that is smaller than Po. The pressure outside is higher than the pressure inside, and we expect inflow, and we expect here inflow of fresh air. So we see that stage 3 now is a more complex case where the flow structure corresponds to both inflow and outflow of fresh air at low elevations and outflow of smoke at high elevations in the vent. And finally, if we are in a situation of a fire that transition, for instance, to flashover, and we have the smoke is pushed towards the floor of the compartment, then we can reach the stage 4 scenario where we end up with a single layer, and the pressure outside is a single curve, is a linear curve, and the pressure inside will be also a straight line, a linear curve, and these two curves will intersect at the end. So this stage 4 scenario is a typical post-flashover situation in which ZD goes to 0. All right, so let's try to come up with some expressions for m dot in and m dot out. We're going to first consider the simplified case of one layer description of the compartment fire. So we're going to assume basically that we are in the case 4 situation where conditions inside the fire room are quasi-uniform. We can describe the temperature inside the fire room through a single value called Ti. We don't need to differentiate between the lower layer and the upper layer. Here we assume basically that ZD is close to 0 and the smoke is at the floor. So the temperature conditions inside the fire room are described through Ti, and Ti corresponds to the mass density ρI. Now, through the ideal gas law, you will remember that ρI goes like 1 over Ti. So the buoyancy of the flow will be related to mass density changes. But when we talk about the mass density ρI, we are talking in the context of a fire, we are talking about the temperature Ti of the smoke. So here we assume a one-layer description, and we also assume that the vent is small. So we're going to characterize the vent by a single elevation Z equals Z capital O. The capital O means opening. Okay. So bear with me on the notations. The small o for P means outside, small I for P means inside, or for rho or for T. But for Z, the capital O means opening. All right, so the question is whether we have inflow or outflow for this small vent. And this question of whether we have inflow or outflow is answered by comparing the elevation of the vent ZO to the neutral plane elevation Zn, which is the location where the pressure inside and the pressure outside straight lines cross, as shown on the sketch on the right. Before we move on to proposing some expressions for the flow rates, let me come up here with an expression of delta P, the differential pressure between the fire room and the outside. So we can write Pi at elevation Z equal to Pi at elevation Zn minus rho g h, or minus rho I g times the distance from Zn to Z. Similarly, we can write that the pressure outside is equal at elevation Z is equal to the pressure outside at elevation Zn minus rho outside times G times Z minus Zn. Okay, so again, this is the hydrostatic pressure variations, And the only difference between these two expressions is that the pressure changes with through a delta P that is proportional to rho I inside the fire room, whereas outside of the fire room, the pressure variations are proportional to rho O, the mass density of air outside of the fire room. So if delta P is defined as Pi minus Po, we see that delta P can be expressed as a delta rho times G times the delta Z, okay, the Z minus Zn. Okay, so the Z neutral elevation, Zn elevation, the neutral plane elevation is a convenient reference when you want to express delta P, because again, the pressure Pi Zn is equal to the pressure Po Zn. And so these pressures drop from the delta P expression. All right, with this in mind, now we can propose an expression in the case where we assume, for the mass flow rate, in the case where we assume that the elevation of the vent, ZO, is above the neutral plane elevation. In that case, Pi is greater than Po, so we now expect outflow. Okay, and we can express the delta P at ZO as delta rho times G times the delta Z, where the delta Z is the change in elevation from the neutral plane to the location of the vent, ZO. Okay. The Bernoulli velocity is square root of 2 delta P divided by rho, where the rho is the rho of the material that goes through the vent. So if we have outflow, it's rho I that needs to be used in the expression for the Bernoulli for the Bernoulli velocity. And finally, at the bottom of the slides, you have the mass flow rate m dot out, which is equal to the flow coefficient CD times rho I times the square root of 2 delta P over rho times the Bernoulli velocity times the surface area of the vent A sub O. And this is reformulated as given on the slide here. So this expression is a very useful expression for the mass flow rate through this small vent, provided that we know the temperature of the smoke. Okay, we are going to need an expression for rho I that we get from the ideal gas law as a function of the temperature Ti of the smoke, and provided also that we know the neutral plane elevation Zn. Presumably, we will know the elevation of the vent ZO, we will know the surface area of the vent A sub O. The flow coefficient can be estimated as 0.7 unless we know better. So we know everything except for the temperature of the smoke that in this set of slides I'm going to assume known. So I'm going to assume that rho I is known through the temperature of the smoke Ti. So the real unknown quantity at this point is the neutral plane elevation Zn. Here on slide 14, now we are looking at the other case where ZO is smaller than Zn. That means that the vent is below the neutral plane elevation and is at a location where the pressure Pi is smaller than the pressure Po, and therefore we're now expecting inflow from outside into the compartment. And the delta P can be again expressed as a delta rho times G times the change in elevation. But the change in elevation is counted now from ZO, from the vent location to Zn, to neutral plane elevation. The expression for the Bernoulli velocity is still the square root of 2 delta P divided by rho, but now the rho is the rho of the material that is crossing the vent, and this is outside air that is coming through that vent. So rho in the denominator of the square root expression for the Bernoulli velocity is rho O now, instead of rho I in the previous slide. In fact, finally, the mass flow rate in is equal to flow coefficient times rho O times the Bernoulli velocity times AO. And you can see the expression at the bottom of the slide. And this expression again can be used provided that we know rho I through the temperature of the smoke Ti, and provided that we know the elevation Zn. So the question now becomes, what is Zn? Okay, and if we are doing hand calculations, we will have Zn coming from a steady state assumption. So let's look at this in the context of a compartment that now has two vents. Okay, and this this compartment, we're going to assume steady state. If we assume steady state here, that means that assuming that the temperature inside the vent Ti is greater than the temperature outside, steady state means that the lower vent will correspond to inflow of outside air, and the upper vent will correspond to outflow of inside material. Okay. And the kind of theory that we're going to develop here is the classical theory used to describe HVAC system, heating, ventilation, and air conditioning system. This corresponds to the winter scenario. In the winter scenario, you are heating your house or your building, and the temperature inside is higher than the temperature outside. There is a similar problem for the summer scenario. In the summer scenario, the temperature inside the structure is smaller than the temperature outside, and therefore, in that case, you would expect a reverse flow direction, where the upper vent will correspond to inflow of outside air, and the lower vent will correspond to outflow of inside gas. All right, but let's go back to our scenario of interest here. In a fire corresponds to a winter scenario. The temperature inside the fire room is higher than the temperature outside. And we are looking at steady state, and we are still in the framework of a single layer description of the conditions inside the fire room. And the vents are assumed to be small. So the lower vent is at a location Z01, and the upper vent at a location Z02. We have the expression of the mass flow rate for the inflow vent and the outflow vent that are given here. These are just simple expressions adapted with the new notations from the expressions that we discussed a few minutes ago. Okay. So these expressions are known and could be used provided that we know Zn. So Zn is the problem here, is the quantity that is unknown. So if we assume steady state, we're going to come up with a new constraint, a new relation that is going to be an equation for Zn. This is what the bottom of the slide shows. So if m dot in is equal to m dot out at steady state, we can write, after some simplification, that we can write the expression that is shown in the slide, that is an equation for Zn, and that can be solved for, and we can go to the next slide, and this is the solution for the neutral plane elevation Zn. Once the neutral plane elevation Zn is known, I can use that expression in the expression of m dot in or m dot out, and through that substitution come up with the expression of the mass flow rate. Okay, I can work with m dot in or m dot out, I would get the same result. And what we have on this slide here is the expression for the mass flow rate for that system, and we see now that we have an expression that depends on the surface area of the vents, AO1, AO2, depends on the flow coefficient for each vent, CD1, CD2, depends on the change in elevation from the lower vent to the upper vent, ZO2 minus ZO1, and depends also on the mass density rho I that corresponds to the mass density of the gases inside the compartment. In fact, it is also proportional to square root of delta rho O minus rho I, because what drives the flow, again, is natural convection. So the flow is driven by a change in mass density as shown by this expression. Okay, so we will see an example of this when I'm back in class. I'm going to keep this discussion with the same kind of problem with slight variation in the setup, where we're going to apply this kind of concepts and expressions to the case of smoke extraction through a ceiling vent. So here I have still a compartment described with our single layer model and two vents, but one of these vents is a horizontal vent on the ceiling. But other than that, this configuration looks very much like the previous one. The lower vent corresponds to inflow of fresh air, and the upper vent corresponds to outflow of supposedly smoke in the case of a fire. Okay, and we would like to calculate how much mass goes through our ceiling vent. So we again have expressions that are similar than the ones that we had before, except that we have new notation. So our lower vent is located at 0, 1 equals 0. Our upper vent is located at 0, 2 equal capital H. So capital H is the height of the ceiling. Other than that, these expressions are similar. We again want to solve this problem by hand, so we are going to invoke steady state. M dot in is equal to M dot out at steady state, and this provides an equation for the n. And we see here on this slide 20 that once we have the equation for the n, we can write the expression for the mass flow rate. And basically, this mass flow rate expression is an expression for the rate of smoke extraction through the ceiling vent. Okay. Now I'm going to spend a few minutes discussing this expression and its meaning, but we can see here that this expression depends on properties associated with the lower vent as well as properties associated with the upper vent, as well as the smoke temperature through rho I. So here we see that the lower vent, the inflow vent, has properties that will affect the rate of extraction. This might be surprising at first sight. I mean, we expect the rate of smoke extraction to be clearly affected by the properties, especially the surface area of the ceiling smoke vent, but we don't necessarily expect a significant effect from the lower vents. However, this expression shows that the lower vent plays a role. Let me go to slide 22 to try to make this case more clearly. In fact, if you go back to slide 21 and slide 22 are identical expressions for the mass flow rate. They are just rewritten in a slightly different way. The expression in slide 22 is better suited for discussion of the effect of AOI, of the surface area of the lower vent. Let's look at the case where AOI goes to infinity. If AOI is very large, okay, it will not have to go to infinity, but if it's very large, then we can easily see that we get an expression for the smoke mass flow rate through the ceiling vent that becomes now independent of AOI, and that is depends only on the smoke temperature and the ceiling height and the surface area of the ceiling vent. Okay, this is called the maximum rate of extraction, meaning that this rate of extraction is not influenced by the surface area of the lower vent, and in fact, the surface area of the lower vent can only decrease the rate of mass extraction. So this is the maximum possible extraction rate for a given ceiling vent. So this is a reference expression. All right, so to make that case a little bit more understandable, here we are going to plot the ratio m dot out divided by m dot out max obtained for a very large lower vent, and we plot it as a function of the ratio of the surface area of the inflow vent and outflow vent times square root of rho O divided by rho I. So on the x-axis, the expression I'm plotting here, this x, is actually unnecessarily complex. You can interpret x as being the ratio of the surface area of the inflow vent divided by the surface area of the outflow vent. I'm saying this because the flow coefficient CDs are about the same at the inflow and outflow vents, and because rho O divided by rho I is of order 1, Okay, it's not going to be exactly 1, but is over the 1. So you can view the x-axis as being basically the ratio of the surface area of the inflow vent divided by the outflow vent. And we see in this expression of m dot out divided by m dot out max that comes from the previous slide that this ratio takes value close to 1 when AOI is indeed large. And what we mean by large is AOI is at least twice the surface area of the ceiling vent. So this is a design criterion that you can find in the SFP literature and in standards, is that when you want to design a smoke control system using ceiling vents, you want the surface area of the ceiling vents to be large, and you want the surface area of the makeup air vents located at the floor to be twice larger. Okay, if you do this, basically the efficiency of your smoke venting system is above 90%. On the other hand, if the makeup air vents located close to the floor bringing fresh air into the room are too small, then the efficiency of your system will be limited and will be lower than 90%. Okay, so this simple theory helps us find design criteria for the conception of a smoke venting system. Okay, let's look now at the effect of the smoke temperature. So we're going to look at the expression m dot out max obtained for a large enough value of AI. So AI, the inflow vent, the makeup air vent surface area is supposed to be at least twice larger than the surface area of the ceiling vent. So we're looking at m dot out max as a valid representation of the extraction rate of smoke through the ceiling vent. And we want to look at the effect of Ti. So we have this expression that is formulated here as a function of square root of rho I divided by rho O times square root of 1 minus rho I divided by rho O, where rho I divided by rho O is equal to TO divided by Ti. So again, we see that through the ideal gas law, the mass density rho I is related to the temperature of the smoke Ti. If I plot m dot out max on the y-axis as a function of Ti over To on the x-axis, I find a curve that is a curve that first goes up, reaches a maximum for a value of Ti about twice the value of To, and then finally decreases. It's an interesting curve because the fact that the curves goes up, the fact that the mass flow rate of smoke through the ceiling vent goes up if the smoke is harder makes perfect sense. Okay, because for a hotter smoke we expect more buoyancy, and if the flow is more buoyant, we expect the mass flow rate to go up. So we see as the ratio Ti over To goes from 1 to 2, we see a very strong increase of the mass flow rate, and that's driven by buoyancy. I think this is pretty intuitive and makes sense. What's less obvious is that we're going to reach a maximum for temperature Ti that will be about twice To, and if To is 300 K, for a temperature of the smoke about 600 K, we reach a maximum, and then the mass flow rate goes down. And this is due to the fact that the mass flow rate is mass density times velocity. So as we increase the temperature Ti, we make the flow more buoyant. That means the buoyant velocity, the Bernoulli velocity in this expression goes up. Okay, and that corresponds to higher mass flow rate, yes. But at the same time, the mass density rho I goes down. So we have basically conflicting effects where the velocity goes up because we are more buoyant, but these gases are less dense, and so the mass density rho I goes down, which would have the tendency to drive the mass flow rate to lower values. So we see that we're going to go for a peak, and on the right-hand side of that curve, we are dominated by the negative effect of temperature on mass density, and the mass flow rate extracted by the ceiling vent will be less. So basically, we get an optimum extraction rate for temperature of the smoke of 600 K. All right, so I think this is the last example I want to discuss as part of this video. We are still looking at the one-layer description, so we have uniform conditions inside the compartment, but now I'm not going to limit myself to small vents anymore. I'm going to look at a large vent, and this vent has a width WO and a height HO. Okay. And so this vent, as far as elevation goes, starts at z equals 0. That's the floor. That's where we have the seal of the vent. And the soffit of the vent, the maximum elevation of the vent, is at HO. Again, capital O for opening. So we're going to calculate the flow through this vent, and we're going to consider three cases. First, we're going to consider that Zn, the neutral plane elevation, is smaller than 0. That means now that through the entire vent, the pressure inside will be greater than the pressure outside. So we are going to have outflow of inside gas through the entire vent. Then we are going to look at the opposite situation where Z neutral is greater than H above. And that will correspond to a situation now where the pressure inside is lower than the pressure outside, and we're going to have an inflow of fresh air through the entire vent. And finally, look at the possible steady-state situation where the neutral plane elevation is between 0 and H above, and we can have both inflow and outflow. So let's look at the first situation. So if the neutral plane elevation that in a complex building may be determined by all the vents present in the building. So the neutral plane elevation may be set up by some other compartments by the entire building structure. So if this neutral plane elevation is smaller than 0, then we expect outflow only through the opening. And we are going to have to calculate the mass flow rate in a slightly different ways, because now the vent has a finite size. So what we typically do is an integration in which the vent surface area is decomposed into elementary surface areas, elementary bands of size of surface area WO times dz. So we're looking at decomposing the vent into elementary elements, into elementary bands between z and z plus delta z. The surface area of these elementary bands is WO delta z, and the mass flow rate through that band is going to be rho times Bernoulli velocity, written as square root of 2 delta p divided by rho, times the surface area of the band. So you can see this through the first expression of m dot out. So we are basically performing a simple integration versus elevation. I'm not giving here the details of the integration, but this can be integrated by hand fairly easily, and you have the result. The result is a complex expression, but again depends on rho I, the mass density of the smoke, so basically depends on the temperature of the smoke, and also depends on Z neutral, the neutral plane elevation. In addition to this, it's going to depend on the properties of the vent now. So instead of depending only on the location of the vent, it also depends on the width and height of the vent. And in particular, what's interesting, we see that the ventilation factor in this expression, the width times the height times square root of the height of the vent, is the ventilation factor, as you know. And this is the first evidence that the ventilation factor that we have used in simple expression, we have assumed that m dot in can be written as 0.5 times the ventilation factor, where we're seeing here that we have an expression that uses the ventilation factor that comes out of this theory. And that's the first evidence that the ventilation factor does indeed play a role in estimating, in the estimation of the mass flow rate through the vents. So this is the first case where Z neutral is lower than 0, where 0 is the elevation of the seal of the vent. Let's look now at the opposite situation where Z neutral is above HO, above the elevation of the soffit of the vent. And we see here that again we have outflow only, I'm sorry, inflow only. Okay, this is a situation where the pressure inside the fire room is lower than the pressure outside, so we inflow only, and we're going to perform an integration of a Z of the classical expression for the mass flow rate, mass density times Bernoulli velocity times surface area of the particular band between Z and Z plus delta Z. When we perform the integration, we again see the ventilation factor playing a role in this expression. Okay, the more interesting case is the case where Z neutral is between 0 and HO, because that means that the upper portion of the vent corresponds to outflow of smoke in a fire scenario, and the lower portion of the vent corresponds to inflow of fresh air in a fire scenario. So let's look at the outflow contribution first. We perform an integration, but this integration now goes from Z neutral to HO, okay, because that's the location of the region where the pressure inside is higher than the pressure outside. So this is the new expression that we have for the outflow mass flow rate, or the mass outflow rate. Again, with an expression that is proportional to the ventilation factor. The inflow of fresh air, the mass inflow rate, is calculated in a similar way. The integration is performed from Z equals 0 to Z equals Zn, because that's the region where the pressure inside is lower than the pressure outside, and we expect inflow. And we get an expression again proportional to the ventilation factor. Now, if we assume steady state and we write m dot in equal m dot out, we find the expression for the neutral plane elevation, and we can plug it in and substitute the expression for Zn into the expression for m dot in or m dot out, and we get the mass flow rate m dot in equal the mass flow rate m dot out with the expression given at the bottom of the slide. Again, an expression that depends on the temperature of the smoke through rho I and the ventilation factor. Okay. All right. So we can compare this expression to the expression 0.5 times the ventilation factor that we've used previously in the class, and we write this expression as a function of rho I, or even better here as a function of Ti, the temperature of the smoke in units of Kelvin. And we see that provided that the temperature of the smoke is above, let's say, 600 K, the m dot in is indeed equal or is close to the usual expression 0.5 times the ventilation factor. So the simple theory here, valid in the case of a single layer description of the gases inside the compartment. This simple theory shows that if the temperature Ti is high enough, let's say above 600 K, then indeed we can write m dot in equal 0.5 times the ventilation factor. If you want more accurate expressions that are valid for two-layer description of the gases inside the fire room, and are valid also for lower temperatures, well, you need to use the theories that are described either here in this part 1, or that will be described in the next set of slides in part 2. But I'm going to stop this discussion here. All right, thank you very much.